This is lecture on Chapter 4. Chapter 4 deals with bonding in compounds, ionic bonding and covalent bonding, which is partly what we left off talking about in Chapter 3. So let's look at ionic bonding first. Ionic bonds are the attraction forces between cations and anions. We know that these are oppositely charged, and there's an attraction. We do say that opposite charges attract, and like charges repel. So the ionic bonds are the bonds between the electrostatic attraction between the cations and anions, and that's what holds together the ionic compounds. They must be electrically neutral, which means that I have to write the formula for the compound in such a way that my total positive charge has to equal the total negative charge. In this case, as you see here, in the crystal of sodium chloride, I have a sodium ion bonded to each chlorine ion in turn. So every chlorine is bonded to a sodium and a sodium bonded to a chlorine. That's a 1-to-1 ratio because I have a +1 ion and a -1 ion. This changes when you have different charges, so a +2 and a -1, or a +1 and a 2-, etc., etc. But the basic idea behind that is that the bonds, the ionic bonds, they have to be electrically neutral, which means that the total negative charge has to balance the total positive charge. Covalent bonds, on the other hand, they occur when electrons are not given or taken completely, but they are shared between two atoms. The electrons are shared between two atoms, and they can be shared equally or not equally. We'll talk about that in a little bit. But a covalent bond is different from an ionic bond, but because the electrons are shared and not totally given off or totally taken to form a complete ion, and a positive ion and a negative ion. So think about if these are my two nuclei and they are covalently bonded to each other. They are sharing some electrons, and these electrons are spending time, most of their time are spending it between these two nuclei of the two elements that are sharing them. Now they might, for a little bit of the time, they might go in other areas around, but most of the time they are shared between the two nuclei, and that's what the covalent bond is this bond between the two elements that is shared between these two electrons. It's caused because of the sharing of those two electrons. When we talk about covalent bonds, there are two different kinds, or two groups. We divide them into polar covalent bonds and nonpolar covalent bonds. What does the polar mean? Well, the polarity depends on how well the electrons are shared, how equally they are shared between the ion, or between the elements. In this molecule, for example, I have hydrogen and a chlorine. This is not an ionic compound because hydrogen it's actually a nonmetal, and so is the chlorine. So this is a covalent bond. However, if you look at these two, it's a diatomic molecule, meaning it's made up of two elements. These are not the same elements, so they do not share those electrons equally. It just so happens that chlorine likes the lion's share of those electrons. Think of this kind of as a tug of war. Because I don't have the same ion, or the same, I keep saying ion, because I don't have the same element over here, those electrons are not shared equally. I have different elements, and therefore the ability of these elements to attract those electrons to themselves is different. Chlorine, it just so happens that it wants those electrons more than the hydrogen does. So those electrons that are being shared between the hydrogen and chlorine end up spending a lot more time or closer to the nucleus of the chlorine than they do to the hydrogen. Now think about the fact that we are sharing electrons here, which means that they're sharing negative charges. If that negative charge spends more time around the chlorine than it does the hydrogen, you will have a little bit more negative charge around the chlorine than you do the hydrogen. It's not a total negative charge like it would be with a sodium, for example, if I had a sodium here instead of a chlorine, because the hydrogen doesn't completely give up that electron. So it has a negative charge, but we call it a partial negative charge, and we denote it with a delta. So this is a Greek letter delta, which is a partial negative charge on the chlorine. And then because the hydrogen has kind of a lack of electrons for most of the time, meaning it acquires a partial positive charge, we call that a delta positive on the hydrogen. Now, anytime we have a separation of charge like this, we call this a dipole moment. And we denote it with an arrow, just like this, where the head of the arrow is pointing toward the partial negative charge, and the other end of the arrow is pointing toward the partial positive charge. Once again, this is not as drastic a separation of charge as you do to form ions, because for those ions, you take that electron and you completely remove it and give it to the chlorine. They're still sharing those electrons, but that electron tends to spend more time around the chlorine than it does the hydrogen. Therefore, it gives it a partial negative charge because the electron is negative, and hydrogen, because it's now those two electrons that are being shared spend more time towards the chlorine, it's left with a partial positive charge. This means that every time, there's a dipole moment that forms from the separation of charge, or the partial separation of charge, and that dipole moment means that this molecule is called, we call it polar. It's a polar molecule. I have a polarity, which means that I have a polar dipole moment, and therefore this is a polar covalent bond. It's a polar bond, it's a polar molecule. The difference between the different types of covalent bonding can be explained by the idea of electronegativity. So what is electronegativity? The electronegativity is the ability of an atom to attract electrons to itself. The better it can do that, the more electronegative it is. So let's look at the periodic table. This is my periodic table. And the weight, there are values associated, electronegativity values associated with most of the atoms. And we will just focus on these. And when we have to do problems, you will not have to memorize all of these values. They will be given to you. But how do we determine what is the trend in electronegativity? I always remember it this way. Remember when I talked about the trends in periodic table, and we talked about ionization energies and atomic radii? Well, this is another trend. And it's easier for me to remember that fluorine is the most electronegative atom, and everything else going down or across is going to decrease. So the fluorine is the most electronegative atom. What does that mean? It's the atom that has the highest ability to attract electrons to itself. So fluorine is going to have the largest partial negative charge out of all these elements that are going to form covalent bonds. So the fluorine bonds that contain fluorine are going to be the most polar bonds because fluorine is the most electronegative. Once again, electronegativity is the ability of an atom to attract the electrons to itself. A high value means it really wants those electrons. A low value, like these elements over here, which is group 1, they don't have very high electronegativity values, and we know that because they give up that electron way too easy to form an ion. There are different ways we can figure out whether a bond is polar or nonpolar, and here is how we tell. If a bond type is pure covalent, the electronegativity difference between bonding atoms is zero. This only happens if we have diatomic molecules that are made of the same element. Hydrogen, for example, H2, O2, F2, I2, etc., etc. So if I have a covalent bond that is made of two atoms of the same type, so this H2 is made up of a hydrogen bonded to another hydrogen. Well, because I have the same element, those electrons are shared equally because they have the same electronegativity value. And therefore, if they have the same electronegativity value, the difference between their electronegativities is going to be zero. And that means that I have a pure covalent bond. In between these, I will have a polar covalent bond. And here's kind of the rule of thumb. If you have an electronegativity difference between the atoms that is less than 0.4, so from 0 to 0.4, we consider those mainly pure covalent bonds. If the electronegativity difference, remember it's a difference, not an addition, if it's between 0.4 and 1.8, then I have a polar covalent bond, which means that I have a separation of charge. One of the elements is more electronegative than the other. Water, for example, if I do water, it's a polar covalent molecule because oxygen is much more electronegative than hydrogen. So if you look back over here, oxygen is 3.5 and hydrogen is 2.1. So the electronegativity difference between these two is 1.4. And if I go over here, oh, I fall between 0.4 and 1.8, so it must be a polar covalent bond. That tells me that water has, the OH bond in water is polar covalent. If the electronegativity difference between the atoms that are bonded is very large, meaning larger than 1.8, then what we get is an ionic bond. As you can see, this is a continuum of the spectrum. We start from pure covalent, and as we change the polarity, or as we change the electronegativity of the elements, we move from covalent to polar covalent, where we have a partial separation of charge, and then all the way to the ionic bond, which is a complete separation of charge. So we move from equally sharing to unequally sharing because one of them is more electronegative than the other, but they're still sharing, to complete separation of charge, complete give and take of the electron. Sodium completely gives the electrons and oxygen completely takes them. So this is kind of a continuum from pure covalent bond to all the way to the ionic bond. Therefore, at the boundaries between these, it can get a little bit difficult to tell whether you have one compound or the other. But the most important thing is to know how to do the electronegativity difference when you have the electronegativity values given to you. And remember, it's a difference. And once you do that, whatever falls very close, let's say it's 1.8 here, well, it could be a polar covalent or it could be an ionic bond, right? It could be either one of them. And then in that case, you consider the types of atoms that are involved. If you have a metal and a nonmetal bonded to each other with an electronegativity difference of 1.8, then you would have to say that that bond is an ionic bond because I have a metal and a nonmetal. If it is an electronegativity difference of 1.8, but you have two nonmetals bonded together, then you would say it's a polar covalent bond. It's a very polar covalent bond. That is kind of how you can work through these. And we will work some of these problems together. But this ends this section of Chapter 4, and then we will continue for the next section with learning how to name and write ionic formulas and eventually covalent formulas as well, knowing the elements that we are given.